Assalamu alaikum. So we'll be continuing from where we left over yesterday. Now, up until our last lecture, we studied about phenol, the reactivity of phenol, then the acidity of phenol, how much acidic it is, and the comparison between the acidity of ethanol, water, and phenol. Then we covered about the reactivity, or like the difference in reactivity between phenol and benzene, that phenol is more reactive than benzene, because in order to undergo nitration reaction, benzene requires a bit more temperature and concentration of a nitric acid needs to be greater, or the nitric acid needs to be concentrated. Then we studied about phenylamine as well, where we saw that phenylamine was actually a bit like further, like it was a one step next reaction, which was like after forming like nitration, after nitration of benzene occurred, if we added tene as a catalyst with concentrated hydrochloric acid and heat, we would get phenylamine. Now we also observed that for phenol and phenylamine, both phenol and phenylamine, they react with bromine. So they react with bromine solution. So if this is, let's say, our phenol, and let's say this is our phenylamine. Now, as I mentioned earlier, that we don't know their colors, because at like in room temperature, or in like in the general solution in natural state, they're colorless. They're colorless. So you're colorless. Now, what happens if we add in, like, with both of them? This is colorless. Let's say we added, like, we don't know, there might be either this, like in the container, either this is present or that is present. Like, let's say we actually don't know who is present there, but we know some sort of organic substance is present. Okay, some sort of organic substance is present. Let's say there can be some alkane, there can be alkene as well. Let's say there is alkene as well. Like, we are guessing that there might be alkene as well, because all the organic substances, they don't have any color. So from our, like, from the outer observation, we would see that just is, let's say, like, it has a like watery color. Like, we cannot actually assume what is inside it until and unless we like have some filtration. Like, for example, while we are in like websites, let's say, we filter out like some sort of like criteria. Let's say we want to buy, or we want to see the product category from this sector or that sector, or at a price range of this. So until we also categorize, or we also filter this, like the, or let's say reduce the amount of like assumption. Let's say we have what the organic substances are alkene, then benzene, then we have halogenyl alkanes, the nitrile compounds, carbonyl compounds. Now we have also, like, in benzene we have some subcategories, phenol, phenylamine, like this sort of things. Now, how can we be sure like which was actually produced? Let's say after reaction, we are assuming maybe, like, maybe there could be phenol, phenylamine, or alkene, or any sort of other organic substances. So in order to, like, in order to be ensured that, okay, this is, or in order to narrow down our, like, let's say, like, range of products, in order to like narrow down our elements, because if we have vast amount of like, for example, if we have alkane, like this much of possibilities, that then we need to individually test them, isn't it? So our, like, chances of error would be more, because we need to at that time have to see, okay, by replacing reagent, is it this one? Okay, no, it is not. Is it this one? No, it is it this one? No, is it this one? Okay, it might be. So before, like, instead of doing that, what we can do, we can apply a reagent, like, at once, and either one or two or three of them would react, and we'd be sure, okay, any three of this product will be present here. Now from here we'll be moving forward. So we know bromine reacts with alkene as well, because bromine is what, brown color in solution, bare to aqueous. So that is brown color in solution. When we add it with alkene, it decolorizes alkene. Okay, like alkene decolorizes bromine because alkene reacts with bromine. So if no more bromine is like in this situation, that means no more brown color solution will be present there. Hence, alkene decolorizes bromine. So in that way, we will be able to understand, okay, there is alkene present. But if no decolorization happens, that means there is no alkene. So this also happened. Let's say no decolorization happened. That means there is no alkene. Now, what happened? Let's say white precipitate was formed. After adding bromine, white PPT was formed. Now we are sure that either of these two components are there. Why? Because when we add bromine with each of them, they react and form bonds. Like each of the phenol, like each phenol and each phenylamine, they tend to undergo same sort of reaction, forming same type of bond with bromine. Okay, so both undergo this type of reaction, like the electrophilic substitution, and both react with bromine. Hence, the brown color of, or the orange brown color of the bromine water is now turned into white precipitate. That means if initially it was, let's say, some sort of this brown color solution, now the brown color solution, it changes, it decolorizes, but at the same time we would see some sort of, let's say, how do I draw white precipitate? Let's say draw with some other color. Let's say just for the thing, let's consider that this is actually white precipitate. Okay, so we will be seeing that white cloudish sort of precipitate is being like formed or sedimented to the like bottom. So that way we will be sure, or our bucket of list will be narrowed down to only just phenol and phenylamine. So from now is it like, it is like so much easier, like it will be so much easier from now, because now we won't be like requiring to deal with many reagents, because we're just like either of them, if we are able to like if we are able to identify any of them, phenylamine and phenol, since we know either of them is present here, now in like inserting or introducing any such reagent which actually reacts with any one of them, we will make our work done, isn't it? So our today's task is to distinguish phenol and phenylamine. Now, how do we distinguish them? Let's say we took the same sample where we are not sure actually which one of them actually is present here. So for actually assuming either of them is present. So in our like last lecture, in the third part of the like organic chemistry, we saw that when we introduce sodium, it reacts with our phenol. Why? Phenol was acidic. So phenol has a characteristic of donating H plus ion in the solution. Okay, so that acidity sort of reacts with sodium. That means in phenol, we will be able to see, let's say if this is the case and we added sodium, then our product would be ONA, where we can also like, let's say we can also just give the like charges on the ions, and with that hydrogen gas will be produced, isn't it? Now obviously this does not have any color, this one does not have any color, this is also colorless, but in the solution we will be seeing, since the gas is produced, if underwater some gas are produced, what do you see? Bubbles, isn't it? So we will see bubbles rising. That will make us clear that okay, hydrogen gas is formed. That means this was actually phenol which reacted with sodium. Then you must be asking, what about phenyl? Phenylamine. Phenylamine actually does not react with sodium. So this one plus Na has no reaction. No reaction. Okay. So remember this part. This has no reaction. That means no bubbles formed due to phenylamine. Another one could be like, this was one of the reaction. Okay. Now the second possible distinguishment could be add litmus paper or To be more specific, blue litmus paper. Now, why did I mention blue litmus paper? Because phenol is acidic. That means our phenol will turn this blue litmus into red. Why? Because about litmus paper, we know for acidic, it has a color like acid. For indicators or in litmus paper, acid shows color of red, and alkalinity or alkali, or which are base, they tend to show what? These are for acid. Acid shows red color, and alkali, they show blue color. Like if this is our pH, let's say pH chart, this is our pH of 7 neutral. Okay, this is pH of 7. Towards the right, you would see it turns like if any indicators or any pH chart we see, observe, also in the, like let's say like if we search in the Google internet, like on the internet, or if we see in the books, you would see towards the right where pH value increases, it's like the color becomes blue, or like, yeah, the color of the paper, the pH, the litmus paper becomes blue, and towards the left it becomes red. Now, two types of litmus paper exist. One is blue litmus, another is red litmus. Blue litmus are used in order to identify like acid. Now, blue litmus paper, when they're submerged into alkali, okay, blue litmus paper, so let's say this is our blue litmus paper, when they're submerged into alkali, we don't see any changes. Why? Because alkali causes the blue color, so it will remain unchanged. But if we add the blue litmus paper into an acid, what happens? The color becomes red. That means there is the presence of acid, which causes the pH to decrease. Okay. Now, if we appear, let's say a red litmus paper, what happens when you submerge it? Like the vice versa happen. If we submerge it into acid, the color does not change. Okay, because acid causes the red color. Now, when we submerge it into an alkali or base, the color changes to blue. Why? Because like that's what it is. It is causing, it increases the pH value. So appearing or introducing a blue litmus paper to our solution would turn what? Would turn a pH, like the phenol, due to the phenol, the blue litmus paper would be turned to red. But due to NH2, the phenylamine, this is like this won't change the color. Now, yeah, if this does not change, then phenylamine. Why? Because phenol, like the phenylamine, it is like sort of alkaline. How can we prove that? Now, if we, let's say we brought two litmus paper in this case, okay. Let's say instead of blue litmus, we also introduce red litmus in this situation. We have two of this litmus, okay. Now, you guess what will happen just if the color of this one changes and this one didn't change. Okay, this one remained what it was. What happened? What would you understand? Let's say there was the solution, and in the solution you submerged both of this litmus paper, and only the blue color got changed. Red color remains same. What would you understand? Like obviously it's an acid, because acid causes that color to change, and for this one, obviously it's red in color, and that's because of the acid. So acid won't change the color of red litmus paper, but it will change the color of the blue litmus paper. Like it is for something like that. Let's say this red litmus paper also have some acidic component in it, and we know acid does not react with an acid. Acid reacts with a base. So that is what it represents. Now, if in a solution the other way happened, let's say the blue litmus didn't change, rather the red litmus turned blue, that would show it was an alkaline solution. NH2 would do the same. NH2 would how do I define? Yeah, NH2, if NH2 was present, then the red litmus paper would have been turned blue. But this blue, like red litmus paper, remains red. Okay. Now, how, maybe I'm making it too complex. Let's say both the color changed. Let's say the red litmus paper color also changed. Now, when does red litmus paper's color change? When there is presence of alkali. And when does blue litmus paper color changes? When there is the presence of acid. So this is due to acid, the color change. and this is due to base. Okay, if both the color changes, that means both acid and alkali is present. That means both phenol and phenylamine would be present. But since only one happened, since red color didn't change, red color remained as it was. So what would it mean? It would mean that there is the presence of only phenol, because the solution is acidic. That's why it changed the color of this one, the blue litmus, into red. So that represents the solution is actually acidic. Okay. And since the red litmus paper color didn't change, there is no phenylamine present. So our solution only contains phenol. Now, there is this term, like this concept, like for example, why phenol tends to react with actually our sodium. There is this concept, obviously, yeah, it is acidic, but why is it so? Because how do I explain? Like usually what happens in an acid, if we add a metal carbonate, okay, metal carbonate, it should react, and it reacts actually. Metal carbonate, it reacts to form carbon dioxide plus water plus salt of the metal. Okay, so let's say we have a acid called HCl and metal carbonate, let's say Na2CO3. That should form carbon dioxide plus water plus NaCl. Yeah, so this is the complex reaction that should have been happened. Okay, but when we, let's say when we also add this sodium carbonate with this phenol, and as we already know phenol is acidic, it should also react, isn't it? Na2CO3, if we added this should also react to form this carbon dioxide, water, and let's say the salt of this bar. But this does not happen. Like no reaction occurs. Now why is it so? Then why does it have a similar sort of reaction with like simple metal? Like why does it react with metal? Because acid also reacts with metal. Acid plus acid plus metal equals to salt plus hydrogen gas. Okay, that's what usually forms. Now why do that occurs? Why does that occur? The main reason is like usually in metal carbonate, when the acid or like acid reacts with in metal carbonate, when acid reacts with this metal carbonate, it does form this carbon dioxide and water. Okay, but like the phenol, why does it usually form is due to the concentration of the H plus being produced. Now, how come that? Remember, phenol, it undergoes dissociation, and I also showed a partial like reversible reaction sign. Remember? So this was the case, isn't it? So that means this acts as a weak acid or much more weak. Like even for carboxylic acids we know they are weak acid. Carboxylic acid, they do react with metal carbonate, but phenol does not. So that means the acidic property of this phenol is even weaker than the carboxylic acid or the weak acids. So we cannot say they are acid. Phenol are not acid, but they are acidic. They show the property of like an acid, or they have the like similar characteristic of acid, but the concentration present is very low. It's very less, okay, in phenol. But then how do this sodium react with the phenol? Because sodium was supposed to react with that H plus ion, like it was supposed to replace that H plus ion. Now here's the thing, that the H plus being produced here, okay, this is enough, like the H plus being produced is like enough for like replacing or making the sodium to lose electron. This much of H plus, like whatever concentration is present there, that is enough for the sodium to react with the phenol by like donating electron, hence forming a bond with the phenol. Like that's the simple logic, and for that reason only the phenol tends to react with sodium only. Okay, now we'll be studying about the formation of amides. Formation of amide. So what are amides? Amides are basically where we have this bond we have studied already, like these were concepts from O levels as well as AS. So this is the concept. AS we studied a bit less, but these are actually based on concepts from O levels, where we studied about the polymerization terms. So in the polymerization topic, we studied about peptide, amide. So this is the amide group. So NHCO bond, NHCO bond. And you would also see in like the biology that they are also like dealing with this sort of structures. So NHCO bond. Now this NHCO bond, this is not just normal NHCO bond. There also exists the presence of our like the benzene ring. The benzene ring also is there. Like the benzene structure is also present there. So one of the part where like this one, the nitrogen, the part with the nitrogen, this should be covered with our like the benzene. The nitrogen's part should be bonded with our benzene. That means we can observe from this portion that it is actually a phenylamine, isn't it? This is the portion of a phenylamine, because phenylamine has what? This is the phenylamine NH2. So one of the hydrogen has been like broken from here. So how the reaction happens? Let's do it. So the reaction actually happens in this way. This is our phenylamine, N, H, and H. And we have here, let's say, the carboxylic acid. So we have studied that amides are formed due to the reaction between what? Amine and like amine group and our acidic group. So amine group and the carboxylic acid group. These two groups must be present there, and they are going to undergo this reaction to form our amides. So the main reaction happens in between these two, like this two group of atoms. Okay, so they actually react, break down from each of the substances, forming our this is the nitrogen, hydrogen, carbon double bond with oxygen. This is our amide group. So this is the amide group. Okay, and we're left with the other side of the product, and this portion, this is going to be eliminated as a byproduct, which is water in this case. Remember our like in O levels also we saw that little like a byproduct is also eliminated because of like water being like as water is produced as a side product or a byproduct. So this is our amide group or amide linkage. Now not necessarily this needs to be an acid. Acyl chloride could also be used. Now who are the acyl chlorides? Acyl chlorides are where carbon oxygen bond is there and there is some alkyl or some other group and we have a chlorine there. These are known as the acyl group. Acyl group. Okay, so for simplicity you can like take the note from for this part like acyl group, because usually they don't declare which are acyl group. Like in books, very few books I've like see in that acyl groups are mentioned clearly which are the acyl groups. So this is an acyl group. Now what happens when this phenylamine come in contact, this phenylamine, this comes in contact with this acyl group or acyl chloride group. So the rest of the thing remains same, let's say. Similar sort of reaction happens between this chlorine and this hydrogen. Okay, and the reaction proceeds. I don't have like any more space towards the right, so I couldn't like continue the reaction to the right side, so I'm continuing towards the like to the bottom side of the page. So consider this. This is our benzene ring, that's our hydrogen. Like the rest of the thing remains completely identical. And this is our like such a situation where the byproduct is in this case what? HCl. Now notice one thing, the structure from the left, like the previous one and this one, just by observing, let's say we didn't or we don't know any of the thing, like we don't know from which of the compound it reacted and what's the byproduct. Let's say we don't know any of them. Okay, we don't know any of them. Then just by showing or just by observing this structure and the product from or the product of this one, both are identical, isn't it? Completely identical, no changes there. That means just by observing the product or the main product, it is not like assumable, or it is not suggestible actually what was the reagents, because in one of the situation we found that acyl chloride was used, and in other situation we found that carboxylic acid was used. That means either using an acid or an acyl chloride, both gave us same product or same amide, isn't it? So that's the thing to be noted. So with more practice, you would get it. Nothing to worry about. Now, how do you form this acyl chloride? Like, we understood about this carboxylic acid. Okay, this would exist. This carboxylic acid, it exists. Let's say this actually exists in natural state. It exists. But let's say we require or we need to form our acyl chloride. Now, how would we form our acyl chloride? So, formation of acyl chloride. So, acyl chloride, it does not exist in its natural state. So before a reaction needs to take place, we need to produce by ourselves in our laboratory experiment the acyl chloride. Okay, so formation of acyl chloride from ethanoic acid. So we actually need to form the acyl chloride from one of the acid. Okay, because other than that, we won't be able to form ethanoic acid is one of the best source to form our acyl chloride. Other sources might be there, but that might be more clumsy and more more work prone. Okay, so now let's say we have this ethanoic acid CH3COOH plus PeCl5. This has nothing to be understandable, because this is just, you need to remember this reactions only. So CH3COOH with PCl, it reacts with PCl5 and produces CH3COCl, is the acyl chloride, and POCl3 plus HCl. We don't have any detailed mechanism and detailed construction of this reaction, so nothing to you don't need to understand what actually which parts are actually reacting in this case. You just need to remember for the simplicity, for the sake of studying, you have to actually keep remember, or sort of, I hate to say that word, but you sort of need to memorize this reaction. Just keep on revising and things will be inshallah easy for you. SOCl2, and this is another part. This is PCl5 and this is SOCl2. So in two ways we can form this acyl chloride. This is actually acyl chloride. Acyl chloride. CH3COCl, the product from these two, the reaction for this two reagent is CH3COCl, which is acyl chloride, and SO2 plus HCl. Okay, this reaction is also given in AS. So AS, we also study about this reaction. So I think that will be more helpful, because we have sort of know this from our A levels, or this won't be much of a difficult thing. Acyl chloride. So in two ways we can form this acyl chloride. Okay, now let's come for the preparation of our benzene diazonium chloride. Now, what are benzene diazonium chloride? Let me write it down. This structure is known as benzene diazonium chloride. Now, don't get scared. It's just a simple structure where this chlorine actually have a negative charge and this is the positive charge. This benzene diazonium chloride is actually an ionic structure. Remember, when do we say a halide, a halogen atom as a halide, like chloride, bromide? When do we say? When they are in their ionic state. So, for example, NaCl, sodium chloride. Okay, but when they have formed a covalent bond, for example, in some sort of organic substance, carbon forms bond, for example, halogenoalkane. Okay, carbon forms bond with a chlorine. In that case, we are saying halogenoalkane or chloroalkane, or we can say we do say also there, let's say alkyl chloride or ethyl chloride, but it's much more convenient to say halogenoalkane. That means chloride doesn't exist. The ion is not present there. It's the single atom forming a bond, covalent bond. But in this case, when chloride actually exists, that is because it has the negative charge. It is acting as an anion there in this case. and forming bond with a positive ion or the cation. Now, how do this reaction occur? So preparation of benzene diazonium chloride. So initially what happens, benzene, it reacts with concentrated nitric acid. So you will get actually some revised parts, because we'll be like now I'm saying just some portion of this, like previous two to three lectures. Those contents are also included here. So benzene reacting with nitric acid with concentrated sulfuric acid, okay, forming what? It is actually nitration of benzene reaction. So forming NO2. Now, when further we add, let's say, tin, SN plus concentrated HCl with heat, what forms? Phenylamine, NH2. Now, when we add NaN2, which is sodium nitrate, or sodium nitrite actually, NaNO2, sodium nitrite, with HCl and 5 degrees centigrade, okay? This is 5 degrees centigrade, or we can say this should be actually less than 10 degrees centigrade, less than 10 degrees centigrade. So if you give, like if question is mentioned, let's say 6 degree, 7 degree, any temperature below 10 degrees is perfect. But when we are asked to answer, just write 5 degrees centigrade, okay? This reaction or this compound is simply going to form, okay? So this is actually the positive ion, and that is our negative ion, okay? So this is our benzene diazonium chloride. Diazonium chloride, yeah. Okay, now you might be thinking, or just for points to be noted here, if more than 10 degrees provided, okay, more than 10 degrees Celsius is provided, then a little bit of phenol will also be produced. Phenol will also be formed. But we don't know, we don't want that. We just want benzene diazonium chloride. So the temperature must be less than 10 degrees centigrade. Okay. Now comes our preparation of phenol. So far, we actually didn't studied how actually phenol was formed. Now is coming the part how phenol is formed. Preparation. I think if you try to guess why we didn't study so far, by just observing this one, you sort of can make assumption, or you it might be you will be able to make assumption, or you might not be. But actually the preparation of phenol is in this way. At first, benzene, it reacted with concentrated HNO3 with concentrated H2SO4 at 55 degrees centigrade. Okay, now we are having a nitro group. Then it, when added with tin with concentrated HCl, and heat is applied, we get our phenylamine. Now further, when we add sodium nitrite, NO2 with HCl at 5 degrees centigrade, we get what? I'm sorry for the drawing. We get our nitrobenzene. This is plus, this is minus. Now this is the part. When we add our water and heat, that means this is what reaction? This is hydrolysis reaction. So when we hydrolysis our benzene diazonium chloride, we get phenol. See? So that's the main reason we didn't study phenol so far, because you wouldn't have understood how this actually happened. What is benzene diazonium chloride? So this is actually a structure. So one after another, from this to this, from this to this, from this to this, from this to this. After so many transition, we actually are getting phenol. So phenol is not a byproduct, or we don't get in the atmosphere. We need to perform this after 4 consecutive steps. Okay, so that's how phenol is formed. Now let's do some examples. So let's say we have this benzene and we added with it, let's say C6H 5COCl, okay, and AlCl3 with anhydrous condition. Okay, in anhydrous condition, we perform or we are like performing this sort of reaction, and let's say we got some product of this one. Okay, so this structure is actually which one? This structure actually C6H5. This can be like actually seen that this is actually like this is also an acyl chloride, but this is actually this one, COOCl. So this is actually the structure. Okay, that's an acyl chloride with this group there present, but written in the molecular form. And we can observe that AlCl3 anhydrous. That means this is actually happening what? So what sort of reaction? Electrophilic substitution, but what? Friedel-Crafts alkylation. So Friedel-Crafts alkylation is happening here, and that's the reaction actually took place. Now, from here, when we add the concentrate, like the conditions are, let's say CH3, CH2, Cl, okay, with AlCl3 anhydrous, what would be formed? These are questions from like the question paper. So what should be formed here? Okay, and from there, let's say we added Br2 with sunlight. Sunlight also, you can say, like, just I'm saying that use UV. They sometimes mention sunlight, sometimes mention UV. So you need to understand what sort of reaction actually they're trying to like make sense. What sort of reaction they are trying to make sense. So this is the substance so far. And after this one, when we add KCN here, KCN, I don't have any more space. Let's do one thing. Let me erase this portion. Okay, let me erase this portion. So I hope like you got it like in the first, like you have the first diagram as well, like the first starting position. So from here, they're saying that you'd get something when you add KCN in ethanol. Okay. Now, what is this reaction? So the first reaction, they have shown that there's the presence of benzene ring, like or the benzene molecule. When we did Friedel-Crafts alkylation, this sort of reaction happened, which makes sense because one of the like hydrogen will be going out, like will be eliminating, and this carbon, this is actually a carbon, isn't it? This is a carbon drawn in the skeletal form, and for like this structure will be formed. Now, when CH3 CH2 Cl is formed, like made to react with AlCl3 anhydrous, now what sort of reaction is happening? There is also a Friedel-Crafts like alkylation, isn't it? Because this condition itself, it defines the Friedel-Crafts alkylation. And see the product afterwards, that Br2 is being added to the sunlight. That means Br2 after adding and sunlight is given, that is what? Free radical substitution, the reaction from alkane. Free radical substitution is happening place. That means this should react in the side chain, not in the benzene structure. Like this reaction should happen in the side chain. That means here is bromine added. That means this is the new part which will be actually produced due to this Friedel-Crafts alkylation. That means doing back tracing, since this carbon is, or this group is actually on this carbon, that means our Friedel-Crafts alkylation should be over here. So this should be our structure, initial structure. Okay. Now when we add Br2 over here with UV light, obviously this is the product which is being formed. That makes sense. Now when KCN in ethanol is present, what do we know? It actually does what? It actually replaces the, what do I say that? Okay, before that, there is also another part I also forgot to mention. From here, there is another part also. From here, when we add H plus with reflux, okay, this product is formed. This product is being formed where this is, sorry, this is our carboxylic acid. That means this is a reflux H plus. Now we have seen so far when KCN is added, what happens? This reaction